OrderGrad, optimizing beyond the mean with Order-Statistic policy gradient estimation by Parmas et al. If you are training a safety-critical robot or a complex reasoning model right now, optimizing for average performance is actively harming your system. Standard reinforcement learning and policy gradient methods like reinforce or standard GRPO, they optimize for mean expected returns. But in modern AI, the mean is often the exact wrong target. OrderGrad provides a plug-and-play family of unbiased gradient estimators for order-statistic objectives. It allows engineers to optimize for the exact distributional properties they actually care about, whether that is the extreme upper tail for LLM best of K discovery or the lower tail for risk-averse robotics. You can do it all by simply sorting rewards and applying rank weights.
Yeah, it's a fundamental shift in how we formulate the learning signal. It completely changes the math of what a model even considers a success.
Welcome to AI Paper Slop, the YouTube series where we summarize the latest AI and tech papers for researchers and ML engineers. We've got an incredibly practical paper for you today. Our mission for this deep dive is to unpack exactly how OrderGrad works under the hood, look at the computational mechanics because, changing the core math of a training loop usually breaks things, and explore how this dramatically improves LLM mathematical reasoning and tail risk management.
The paper really tackles a problem that is so deeply embedded in standard machine learning pipelines that we honestly almost forget to question it. I'm talking about the objective function, J mean of theta, the expected reward. Whenever we train an RL model, we are essentially taking this incredibly rich, complex distribution of possible outcomes and just compressing it into a single scalar value.
I want to stop right there and just establish why optimizing for that single scalar, the mean reward, is fundamentally flawed in modern high-stakes deployments. Because riding through the paper, they highlight three specific areas where chasing the average just falls apart completely. First, you have inference time generation systems, like language models doing math.
Right.
There, you sample several completions and select the best one using a verifier or a reward model. In that setup, you only care about the upper tail. You want the highest possible quality in that subset. Second, you have safety-critical controllers. Think of a robot navigating a cluttered physical space. There, you care deeply about the lower tail.
Exactly. The lower tail is everything there.
Right. You are optimizing for percentile risk or worst-case scenarios. And third, robust learners that need to mathematically trim out corrupted, high-loss samples from poisoned training data.
Yeah, and when you optimize purely for the expected value, the algorithm becomes, completely blind to the shape of the distribution. An algorithm could achieve a high mean reward by succeeding brilliantly 90% of the time and literally crashing a car the other 10%.
Which is obviously a catastrophic failure.
Right. In a safety-critical setting, that mean is just an illusion of success. And on the flip side, in an LLM generation setting, a high mean might just mean the model is consistently mediocre. It never produces that one spark of brilliant, convoluted logic you actually need for a best event selection.
Okay, let's ground this with a real-world scenario. Optimizing for the mean is like judging a restaurant solely by its 3-star average rating. If you were planning a vital once-in-a-lifetime anniversary dinner, you don't care about the average experience. You want to know if they have 5-star nights. You were doing best of K selection for your night out. You want that upper tail. On the flip side, if you have severe food allergies, you only care about the 1-star food poisoning reviews. That's your lower tail risk. A 3-star average tells you absolutely nothing about the extreme edge cases you actually care about.
That maps perfectly to the problem. The mean is just a flat line drawn through chaos. But the question then becomes, if the mean is this blind to edge cases, how do we actually write an algorithm that can mathematically see and target these specific tails during training? Because standard likelihood ratio estimators, which power your typical policy gradients, they just differentiate long probabilities and weight them by scalar returns. They don't have a built-in mechanism to care about the rank of an outcome.
Which is the core mechanical problem. So let's open the hood on OrderGrad. How does it mathematically solve this blindness? The paper mentions it is based on L statistics, which honestly sounds like heavy jargon. What does that actually mean in plain English?
It sounds intimidating, I know, but L-statistics just stands for a linear combination of order statistics. And an order statistic is literally just taking your samples and sorting them.
Oh, okay. So just sorting an array.
Yeah, exactly. So instead of summarizing a reward distribution by its mean, OrderGrad draws a small group of sampled rewards. Let's call the samples size K. It sorts them from lowest to highest. Then it applies a rank weight vector, alpha. By deciding which ranks get which weights, you entirely dictate which parts of the distribution matter to the gradient.
Okay, so if I have k equals 4 samples, and I place all my weight on the number one rank like the absolute highest score, I'm telling the algorithm to strictly emphasize that high quantile best of k performance for an LLM.
Precisely. And if you place your weight on the lowest rank, you are optimizing for safety and robustness in the lower tail. This gives you metrics like conditional value at risk, or CVR. Spreading the weight evenly over the middle ranks gives you a trimmed mean, which effectively ignores outliers at both ends. What the authors of OrderGrad figured out is how to derive unbiased gradient estimators for these sorted, rank-weighted objectives without requiring you to, rewrite the core machinery of your RL loop.
Well, before we talk about how they keep it unbiased, the paper states this works for both likelihood ratio estimators and reparameterization gradients. Just to refresh the listeners, what is the intuitive difference between those two pathways?
Good distinction to make. Likelihood ratio, or LR estimators, are what you see in standard policy gradients like reinforce or PPO. It's essentially trial and error RL. The model guesses, gets a reward, and we increase the probability of the good guesses. Reparameterization, or RP gradients, are used when you have a continuous differentiable pathway like in variational autoencoders. You separate the random noise from the network parameters, which allows you to backpropagate directly through the samples. OrderGrad actually manages to unify order-statistic optimization for both paradigms.
Let's focus on the likelihood ratio route, since that's what a lot of the LLM engineers listening will be dealing with. For LR, instead of replacing your log prob gradient with a standard reward minus a baseline, OrderGrad transforms the mini-batch rewards into rank advantages. But to keep a gradient unbiased, you need a baseline that isn't contaminated by the sample you are evaluating. The paper mentions an include one subset expectation minus a leave one out baseline. Give me an intuition for that. Why does leaving one out make it unbiased?
Think about grading on a curve. If I compare your individual test score against the class average, including your score.
My own score taints the baseline.
Exactly. The baseline is mathematically tainted by your own performance. If you scored a 0, you drag the baseline down with you, which messes up the relative advantage calculation. But if I compare your score against the average of everyone else in the class, excluding you, it's a pure mathematically independent baseline. Yeah, the leave one out baseline in OrderGrad does exactly this for the sampled rewards. Because it excludes the current sample, it remains completely independent of the score term, perfectly satisfying the strict mathematical conditions needed for an unbiased policy gradient.
That makes total sense. And here's where it gets really interesting for the engineers. The implementation isn't some massive architectural overhaul. It is practically a one-line reward transformation. You just call ordergrad.lstat_advantage on your rewards, pass in your alpha weights, and plug the output right into your standard PPO or GRPO update.
That's the beauty of it. It sits neatly on top of whatever existing RL pipeline you already have.
Okay, hold on. I have to push back here, because whenever someone says a complex mathematical transformation is a simple one-line implementation, there's usually a massive catch. If I have a huge rollout batch, computing probabilities for every possible subset to calculate those leave one out baselines sounds like a combinatorial nightmare. Doesn't sorting massive arrays and calculating subset combinatorics on the fly just grind the RL pipeline to a complete halt? I mean, we're already GPU bound in these training runs.
It is a completely valid concern, and it's exactly why many theoretical RL papers never actually survive in production. But the diagnostic results in the paper are very clear. And the math totally saves us here. The heavy lifting, all those binomial subset probabilities needed for the include one and leave one out baselines, they only depend on 3 static things: the batch size n, the order statistic size k, and your chosen weight vector alpha.
Wait, so none of that depends on the actual rewards themselves?
Exactly. Because those variables are fixed during a training step, the complex rank weights can be pre-computed before you ever look at the rewards. It's like baking a massive batch of cakes. Instead of doing the complex math on exactly how much flour and sugar you need for every individual cupcake as you pour the batter, you pre-calculate the master recipe once at the start. After that, you're just pouring.
So you aren't doing the complex combinatorics on the fly.
Yeah.
You're just applying a pre-baked vector.
Yes. Once you've collapsed the weights, the per mini batch cost is simply O of n log n. It is dominated entirely by the incredibly basic operation of sorting the rewards. Everything after the sort is just a linear pass. The paper's diagnostics show that for a batch size of 10,000, the OrderGrad update takes about 1 millisecond.
Wow.
It is functionally negligible. It will absolutely not bottleneck your GPU.
That is fantastic. Okay, so the math proves it won't fry our compute clusters.
Right.
But math in a vacuum is cheap. If I actually drop this into a massive LLM training run to find that five-star restaurant response, does it actually survive the chaos of real-world reasoning tasks?
The researchers put OrderGrad to a very brutal test to answer exactly that. They did RL fine-tuning on Qwen 3 4B base and Qwen 2.5 Math 7B. The training was done on the math dataset, and they evaluated the models across a rigorous suite AIM 2024, AIM 2025, AMC 2023, Math 500, and Minerva.
That is a serious gauntlet of benchmarks. And they compared OrderGrad against standard GRPO group relative policy optimization and another variant called MaxPO. Now, just to define terms for everyone, MaxPO is a special case of OrderGrad where you only optimize for the absolute top 1 rank. But OrderGrad allows for a more nuanced objective called top M at K. Specifically, they tested top 2 at 4, meaning out of 4 samples, you average the rewards of the top 2. Before we get into the results, let's define the metric they used. Pass at 256.
Right. Pass at 256 means that during inference, the model generates 256 different attempts at solving a math problem. If even one of those 256 attempts arrives at the correct final answer, the model gets a passing grade for that problem.
Okay.
It's a metric that heavily rewards a model's ability to explore diverse, creative reasoning paths.
So how did OrderGrad perform against standard GRPO on that metric?
The results were striking. OrderGrad's top 2 at 4 improved the pass at 256 metric by 0.092 on the Qwen 3 4B base model compared to standard GRPO.
An absolute improvement of nearly 10% on a base model just by changing a one-line reward transformation? That's massive.
It is, and the most crucial part is why it improved. It completely avoided the diversity collapse that standard GRPO suffers from. In standard GRPO, as you scale up the number of samples at inference time generating 64, 128, or 256 samples, the performance often plateaus or even drops. The model loses the diversity needed to explore different reasoning paths. It just starts spitting out the exact same, slightly above average answer 256 times. OrderGrad maintained that diversity, allowing the pass at 256 score to keep scaling smoothly.
I'm still stuck on one architectural choice, though. If the entire point of this is to find the absolute best reasoning trace, the singular brilliant path to the correct math answer, why are we averaging the top 2? Why use top 2 at 4? If we want the best, why not just use MaxPO and strictly reward the absolute top 1 rollout?
It's a great question, and it highlights a classic problem in machine learning: the exploration-exploitation trade-off. Taking just the absolute maximum reward is a very sharp, very noisy objective. It creates a highly sparse learning signal. If you only reward the number 1 spot, the gradient jumps around wildly based on whatever lucky sample happened to win that batch. That instability can easily derail training.
So by using top 2 or top 3 out of K samples, you're essentially smoothing out the peak.
Exactly. You are averaging over more high-ranked samples, which significantly improves the signal-to-noise ratio, or SNR, of the gradient estimator. The paper includes a chart that visualizes this beautifully. As you increase M in the top M objective, the estimator noise drops drastically. That stabilizes the training dynamics. But because you are still strictly restricting the weights to the upper ranks, you keep the optimization pressure firmly on the upper tail. You get the best of both worlds: mathematical stability and extreme high-end performance.
So OrderGrad gives us a stable, mathematically sound way to hunt for brilliant reasoning paths. But anyone who has trained reasoning models recently knows about the reward farming problem.
Oh, yeah?
These models love to overthink. To ensure they hit the right answer, they will generate endlessly long, rambling responses, inserting thousands of tokens of filler text before finally spitting out an answer. How does OrderGrad handle competing objectives? If I want to apply a length penalty to stop that rambling, how does this rank-based system cope?
This is where OrderGrad really flexes its muscles because standard methods handle this terribly. In a multi-reward experiment, the authors looked at standard GRPO. If you try to stop endless rambling in GRPO by adding a length penalty, you have to do what's called a scalarization. You literally just sum the correctness reward and the length penalty uniformly across all rollouts.
Which, if I'm guessing, creates a massively confusing learning signal for the model.
It's a complete disaster. The paper shows the scalarization causes degenerate, collapsed short outputs. Because the penalty is applied uniformly, it interferes with the actual reasoning process across the board. The model basically decides it's mathematically safer to just output a short, incorrect answer and avoid the length penalty entirely rather than risk a long reasoning trace that might be correct.
Okay, so how does OrderGrad solve that without breaking the model's ability to reason?
Well, because OrderGrad can target different ranks with different rewards, they used a surgical approach. Using a sample size of k equals 4, they gave the top two rollouts a correctness weight of 1.0. But they gave the bottom two rollouts, which invariably end up being the longest incorrect rollouts, a length penalty weight.
Let me make sure I follow this because it sounds almost too simple. Instead of taxing the whole classroom for talking too much, which makes everyone just stop participating entirely, we only give detention to the two students who are actively rambling the most and getting the wrong answer. But I have to be skeptical here. If you only penalize the bottom two for length, doesn't the model just learn that being long is fine as long as you're in the top two?
Yes, and that is exactly what we want. If a 10,000 token response actually solves a massive complex math problem flawlessly, we don't want to penalize it. We only want to penalize length when it's correlated with failure. The empirical results confirm this works perfectly. This targeted rank weighting preserves the high pass at k solve rate. It stays right up there with the pure correctness baseline, but it entirely eliminates the massive 10,000 token incorrect ramblings seen in the unpenalized baseline. The overall response length distribution completely shifts down, but the model's ability to reason remains intact.
It's fascinating that literally just separating the reward signals by rank completely prevents that catastrophic interference. Okay, we've spent a lot of time on how OrderGrad beautifully shapes the upper tail for language models. Let's pivot entirely. What if our primary goal isn't finding a rare genius answer? What if we're in a domain where our only goal is guaranteeing we absolutely never hit a catastrophic failure?
To explore the lower tail, the paper shifts from language models to a financial portfolio management toy experiment. The goal is to maximize returns using three risky assets: a high-yield asset, a defensive hedge, and a balanced asset plus cash. But there is a twist. During the deployment phase, there is a hidden disaster probability of 35%.
So we are simulating an environment with a severe lower tail risk. To understand CVR conditional value at risk, we need to define it. CVR basically means looking at the expected return of the absolute worst X% of outcomes. Let's contrast standard reinforce, which uses the mean objective, with OrderGrad using a CVR objective. The paper shows that standard reinforce gets incredibly greedy. It chases the normal period drift looking purely at the average and dumps 70.2% of its capital into the high-yield asset.
Right, and in normal times, that looks like a genius strategy. It gets a 14.6% mean return. But because the mean objective is completely blind to the left tail, when it deploys into that 35% disaster environment, the strategy shatters. It loses money in 35.3% of the deployment paths and suffers a massive mean maximum drawdown of negative 18.9%.
It crashes hard. Now, look at the delta when they use OrderGrad CVR. Because it is actively optimizing the lower tail, the algorithm looks at that 35% disaster risk and automatically shifts 59.2% of the portfolio into the defensive hedge asset. Yes, you sacrifice some upside. The mean return drops from 14.6% down to 10.7%. But in exchange, it effectively never crashes. Your major crash risk drops to literal zero. It loses money in only 0.47% of paths.
This perfectly encapsulates the power of order-statistic optimization. The CVR train policy gives heavy mathematical weight to the bad episodes observed during training. It doesn't just average them out of existence. And it's worth noting the paper proves this robust concept works beyond just finance or robotics. They applied it to a robust regression task using corrupted training data.
The poison data experiment.
Yes. By using a trimmed mean rank weight, where you assign 0 weight to the extreme high and low ranks, the estimator perfectly ignores the poisoned outliers and mathematically recovers clean regression lines from heavily corrupted data. The standard mean estimator, predictably, just gets pulled completely off course by the bad labels.
It is so incredibly versatile. Okay, let's wrap this up and synthesize what we've learned today. OrderGrad isn't just a new algorithmic trick. It's a fundamental perspective shift for the entire field of machine learning. By treating K-sample sorting and rank weighting as a computationally cheap 1 millisecond reward transformation, engineers can now surgically target the exact behavior distribution they want. It bridges both likelihood ratio and reparameterization estimators, and it plugs directly into existing code bases without blowing up your compute budget.
It forces the entire industry to ask a very uncomfortable question, like why are we still compressing our rich, complex reward distributions into a single, highly misleading average?
Which leaves us with a final provocative thought for you to ponder. If we now have an off-the-shelf, computationally cheap way to strictly optimize for any specific quantile or tail of an AI's behavior, is the era of benchmarking models purely on average performance officially obsolete? If we can mathematically guarantee a model's worst-case behavior rather than just hoping for the best on average, How will this completely rewrite what we consider a truly aligned AI model?
It's definitely a question every researcher and ML engineer is going to have to answer very soon.
Thanks for tuning in to this deep dive on AI paper slop. Be sure to check out the paper link in the description to explore the code and see exactly how to implement OrderGrad.lstat_advantage in your own training pipelines. See you next time.